Another quiz. What is the probability that a random message that arrives to fall into the spam bucket, assuming that those messages are all drawn at random? And the answer is there's 8 different messages, of which 3 are spam. So the maximum likelihood estimate is 3 over 8. So let's look at this a little bit more formally and talk about maximum likelihood. Obviously, we're observing 8 messages: spam, 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 and 5 times ham. And what we care about is what's our prior probability of spam that maximizes the likelihood of this data. So let's assume we're going to assign a value of pi to this. We wish to find the pi that maximizes the likelihood of this data over here, assuming that each email is drawn independently according to an identical distribution. The probability of the ith data item is then pi if yi equals spam, and 1 minus pi if yi equals ham. If we divide the data as 1, 1, 1, 0, 0, 0, 0, 0, we can write pi as follows: pi to the yi times 1 minus pi to the 1 minus yi. It's not that easy to see that this is equivalent, but say yi equals 1, then this term will fall out. It's a multiplication by 1 because the exponent is 0, and we get pi as over here. If yi equals 0, then this term falls out, and this one here becomes 1 minus pi as over here. Now assuming independence, we get for the entire data set that the joint probability of all 8 data items is the product of the individual data items over here, which can now be written as follows: pi to the count of instances where yi equals 1 times 1 minus pi to the count of the instances where yi equals 0. And we know in our example that this count over here is 3, and this count over here is 5. So we get pi to the third times 1 minus pi fifth. We now wish to find the pi that maximizes this expression over here. We can also maximize the logarithm of this expression, which is 3 times log pi plus 5 times log 1 minus pi. Optimizing the log is the same as optimizing p because the log is monotonic in p. The maximum of this function is attained where the derivative is 0. So let's compute the derivative and set it to 0. This is the derivative, 3 over pi minus 5 over 1 minus pi. We now bring this expression to the right side, multiply the denominators up, and sort all the expressions containing pi to the left, which gives us pi equals 3 over 8, exactly the number we were looking for. So we just derived mathematically that the data likelihood maximizing number for the probability is indeed the empirical count, which means when we looked at this quiz before and we said the maximum likelihood solution for the prior probability of spam is 3/8 by simply counting 3 over 8 emails were spam, we actually followed proper mathematical principles to do maximum likelihood estimation. Now you might not fully have gotten the derivation of this, and I recommend you to watch it again, but it's not that important for the progress in this class. So here's another quiz. I'd like the maximum likelihood for ML solutions for the following probabilities. The probability that the word secret comes up, assuming that we already know a message is spam, and the probability that the same word secret comes up if we happen to know the message is not spam, it's ham. And just as before, we count the word secret in spam and in ham, as I've underlined here. 3 out of 9 words in spam are the word secret, so we have a third over here, or 0.333. And only 1 out of all the 15 words in ham are secret, so you get a 15th, or 0.0667. By now, you might have recognized what we're really building up is a Bayes network, where the parameters of the Bayes networks are estimated using supervised learning by a maximum likelihood estimator based on training data. The Bayes network has at its root an unobservable variable called spam, which is binary, and it has as many children as there are words in a message, where each word has an identical conditional distribution of the word occurrence given the class spam or not spam. If you write on our dictionary over here, you might remember the dictionary had 12 different words. So here's 5 out of the 12. Offer is secret, click, and sports. Then for the spam class, we found that the probability of secret given spam is a third. And we also found that the probability of secret given ham is a 15th. So here's a quiz. Assuming a vocabulary size of 12, or put differently, the dictionary has 12 words, how many parameters do we need to specify this Bayes network? And the correct answer is 23. We need 1 parameter for the prior, P of spam, and then we have 2 dictionary distributions of any word I given spam, and the same for ham. Now there's 12 words in the dictionary, but this distribution only needs 11 parameters. The 12 can be figured out because they have to add up to 1. And the same is true over here. So if we add all these together, we get 23.